In the last video of our module, we're going to talk about how we actually can make observations of ocean biogeochemistry in the present day. This is often a lot more difficult than it might seem. So for example, I'm showing here a video of the ocean around Antarctica, where there's a lot of important biogeochemical processes going on, like we talked about in the last video, but it can be really challenging to sample, especially in the winter when you have lots of sea ice extending out from the coast and the ice shelves. So how do we measure the ocean? You know, some of this you're familiar with. We've talked some about different ways of measuring the ocean through the course, but you know, for instance, you can measure some things from space, right? So chlorophyll concentration, you're not actually measuring chlorophyll concentration from space, but you can measure ocean color, and that can be converted to chlorophyll concentrations according to in situ measurements. Also, I'm showing here sea surface temperature. These are both from NASA Earth Observatory. One thing that's worth considering is that you know, these images show nice, perfect, you know, compilations. At least for sea surface temperature, there's no gaps at all. For chlorophyll, you do see some gaps from cloud cover and lack of light. But even these are actually, you know, these are monthly images that I'm showing here. You start getting down to daily images, and even from satellites, there's gaps, right? You have clouds, you have times where there's not enough light, for instance, in the wintertime in the Southern Ocean, or the wintertime in the Northern Hemisphere, where you don't have enough light to actually measure ocean color. So you get a lot of information from space, but it's just the very surface, and there's a lot of things you can't measure. So now when we think about actual measurements in the ocean, I showed these images earlier of nitrate. And so this is from the World Oceanalysis. It's a compilation of shipboard data. And you might have noticed that there are these regions with these hash marks where there's some shading. And that shading indicates areas where there's, you know, they're still making an estimate of the surface values, but you have lots of gaps, actually. These are areas where they don't have high confidence because there's not a lot of measurements. There's a lot of interpolation. And so anytime you see a map of global or chemical properties, or global biological or chemical properties, you're looking at estimates. Now, maybe they're very good estimates, maybe they're not, but this is something that is an ongoing field, which is essentially how do you map the existing observations that you have. And so when you sort of peel back the hood and look at how we measure the ocean, you know, a lot of the data that we see for chemistry certainly comes from shipboard measurements. So that's kind of traditionally how we've sampled the ocean. You put out a rosette. Each of those white tubes on this rosette are Niskin bottles. Each of those bottles will be tripped at a specific depth. So this rosette has 24 bottles, and so you can sample at 24 depths and take the water up to the ship and then do your measurements, which is for something quite easy, for other things a lot more difficult. I do a lot of oxygen measurements. You have to be really careful you don't get atmospheric contamination. And you also can have sensors on the rosette, so those will be making measurements as the CTV goes down and as it comes back up. And give a sense of what sort of observational density you get from ships. So the maps I have on the left here are maps of surface ocean PCO2 observations. These are unique monthly observations on the top and total monthly observations on the bottom over the last 4 or 5 decades. And so for the upper map, where you have those dark reds, that's where you have a full annual cycle. So all 12 months of the year measured at any point. So it's not saying you got, you know, January through December of every year. It's saying over those last 4 decades, you've managed to measure at least once in every month in any year. Places where you have that light pink or purple, that's where you've only measured 1 month in any year over, you know, all time. Now surface ocean PCO2, can't do it from every ship, but you can do it from a lot of ships, and they do it from ships of opportunity as well. So that's not even, this is just an underway data set. They're not even having to stop and put bottles down and make measurements. So it's actually less if you look at some other things. I'll show oxygen a little bit later. So, there's lots of places in the ocean where we don't have a lot of measurements, and sometimes we also bias those measurements towards summer, because like if you look here, this is a video from the North Pacific Ocean Station Papa, which is one of these places that has been repeatedly measured over the last 30 years or so. This is actually in June. Right? This is the weather we get in June. This is not bad, but it's still rough. It can be hard to do science in anything that's rougher than this. And so in the winter, you often don't get ships going out here. And so that's why you get these big gaps in these maps of where we have measurements. And so one thing that's happening is that we've got more and more autonomous vehicles going out into the ocean and measuring things. And so autonomous platforms, I should say platforms, not just vehicles. So like a mooring is an autonomous platform. We've got sensors on the mooring, we've got sensors on the cable below the mooring, going down a few hundred meters, sometimes all the way to the bottom of the ocean. And those data can get sent back via satellite, or when you recover the mooring, then you download the data. Also gliders and profiling floats. So here, this is a glider that I deployed out again at Ocean Station Papa. And this is a profiling float that I was deploying in the Kuroshio region outside of, or off the coast of Japan in the Northwest Pacific. So these are all autonomous robots or vehicles, and they can carry sensors to measure ocean properties. So if you've got a sensor to measure what you're looking at, which is not a given, that's hard to do, then you can measure the ocean. And I won't even get into talking about calibrating and making sure those sensors don't drift, but that's a whole other thing that we still are struggling with. So profiling floats is something I work with a lot, so I want to talk a bit more about it, in part because we're fundamentally changing how we measure the ocean and what kind of questions we can even ask, let alone answer. So profiling floats spend most of their time at depth, 1,000 meters. They drift for around 9 days, and then they descend down to 2,000 meters and make measurements all the way up to the surface for a total cycle of about 10 days. So that's sort of the standard way that these work. This is this diagram hasn't been updated in a while. We now use iridium communication, so they only take about 15 minutes to transmit their data via satellite. But these can be changed, the mission can be changed, but the sort of standard Argo, these are called the Argo floats, the standard Argo mission is to profile once every 10 days. They can last for 5 to 7 years. These are driven by buoyancy engines, so this schematic is an idea of what's inside these floats and all the different components, but essentially the floats have their mass. The mass doesn't change, but they can pump hydraulic fluid in and out of their pressure chambers. So they've got a pressurized chamber, and if you pump hydraulic fluid out and inflate this bladder, then their volume will increase. If your volume is larger, but your mass stays the same, you're changing your density, right? So density is just mass per volume, and so if your mass stays the same and your volume increases, then your density goes down, and so then you're lighter, so you can come up to the surface. And similarly, if you pump fluid from that hydraulic bladder then into your pressure housing, you're decreasing your volume, and so then you're becoming denser. You're decreasing the volume, but your mass stays the same, so you become denser and you can sink down. So they use these buoyancy engines to profile up and down the water column. Gliders also use buoyancy engines, but they can steer as well. I'll talk about that in a minute. So Argo program is really revolutionized things. So it started off with just temperature and salinity measurements, and here this is showing the profiles made from Argo floats starting in the early 2000s when the program began and moving forward to present day. And this is just showing number of profiles in a 1 degree by 1 degree box. And so really starting to fill in the ocean, and it's changed our view of ocean circulation, how the ocean takes up heat. It's really kind of been amazing. And so now if you, this globe here is showing floats in different colors. Those different colors, this is the present day, or I guess it's a few years old, but it's the more or less the current distribution of floats. And the colors are different countries. So this is a global program. It's not just U.S. The U.S. floats here are green. There's a lot of green. But, purple's Japan. I think dark blue is either France or India, or France or Germany. I forget. Red is Canada, and there's a large number of countries that have contributed. Sometimes even just a few floats, but it's giving us this global observing system. To not just give us a snapshot, but real-time temperature and salinity. Now, recently, there's been a huge increase in the number of biogeochemical sensors on floats. So now we can measure oxygen. Oxygen started in the early 2000s, but it's really been taken off recently. Nitrate, pH, and then optical measurements that tell us something about biology. So fluorescence, backscatter. Now there's some that measure radiation, essentially, how much light is coming down that phytoplankton can use. And so in this figure, not all of these floats have all these sensors. Oxygen is the most common, and these, this is actually, these are currently active floats. There's been about 1,800 floats with oxygen deployed, totally 1,900 actually, I guess now. Some of them have all 6 sensors of these floats, but there's quite a few now, and that it's starting to really change our view of ocean biogeochemistry. And to give you a sense of how it's really changing things, this is a figure from a paper I submitted a few weeks ago looking at float oxygen profiles versus shipboard oxygen profiles. So in the top plot, that's float profiles. This is in a 2x2 degree bin, and it's just the number of profiles that have been made in a given location in the ocean over the course of Argo. And then below, in the same color scheme, number of profiles, same color scale, are GLODAP oxygen profiles. GLODAP is a shipboard data set of bottle measurements that's been sort of quality controlled. It's really good, high quality data. And you can see there's a lot fewer shipboard profiles. Now those, we generally trust them more, especially these that have been carefully vetted and quality controlled. But it's really changing how we look at the ocean. And to look at this in a different way, this is the monthly oxygen profiles over time. You don't need to worry about the different types of float electrodes or optodes. Those are all just different oxygen sensors. The point is that we are sampling more from autonomous vehicles from just profiling floats than we are from ships by a huge amount, and that's not going to change anytime soon. Certainly we need ships, and I would be the last to say that floats are going to replace them, but we're getting a very different picture of the ocean in much more detail now than we ever were before. In the US and globally, this has really been driven, the biogeochemical side of things has really been driven by 2 large projects, SOCOM and GoBGC. Both of these are primarily funded by the National Science Foundation, although with help from NASA and NOAA. SOCOM, the Southern Ocean Carbon and Climate Observations and Modeling Project. On the left here, this is showing where SOCOM floats are currently active, inactive ones that are dead but return data for a long period of time. And one of the cool things is that, so this map shows where the daily ice edge is from satellite drive data set. These floats work under ice. They come up if they sense that it's really cold and there's likely ice above, then they dive back down, and they'll do that until it's clear that there's ice-free water above. Then they'll come up and they'll transmit all the data from the profiles that are under ice. And so we have this really cool under ice data set that we never have had before, and we're doing lots of fun things with that. On the right hand side, this is a figure from global ocean biogeochemical array. It started just a few years ago, but they're now trying to deploy fully equipped biogeochemical Argo floats globally and fill in what might be a reasonable portion of a sort of U.S. part of a global array, which would be about 500. The goal is to have 500 floats in at a given time, and ideally the rest of the world would contribute 500 as well. These are not like long-term funded projects. I was a postdoc in the SOCOM project back in its first iteration. It's currently finishing its second iteration, so that'll be 10 years, and then we have a proposal in for another 5 years, but I don't know if it's going to get funded. GoBGC sort of was a one-time deal and needs to have a successor. So these are really cool programs, but hopefully in 20 years I'll be looking back at 30, 40 years of float data and not this one brief bright period, but I'm optimistic. And then just to recap, there's a number of other ways that autonomous vehicles have been measuring the ocean. So this is a sail drone. This is another type of robot. These are really large, and they measure biogeochemistry in the upper ocean. Gliders, like floats, but they can swim around. Wave gliders powered by the wave, and even animal-borne sensors. So there's a whole really large range of things that we're able to do to measure the ocean, and it's an exciting time. So if you have any questions, please feel free to reach out.